Bismillahirrahmanirrahim. Welcome to the YouTube channel Electrical Engineering. In this lecture, I am going to demonstrate the equivalent circuit and mathematical model of an induction motor. The equivalent circuit of an induction motor consists of the stator side and the rotor side, and the stator side consists of the stator winding, which has a winding resistance and the leakage reactance. So these are represented by R1 and JX1 respectively. This RC and this JXM correspond to the magnetizing inductance and the resistance which is associated with the eddy current laws. So these are the induced EMFs across the stator side and the rotor side. This is the rotor winding leakage reactance, and this is the rotor winding resistance R2. Now, the equivalent circuit of an induction motor is very much similar to that of the transformer, because in both the transformer and the induction motor, the underlying principle which is taking place is that of the Faraday's law of electromagnetic induction. Here, there are some very important points in induction motor which are not the same in case of the transformer. So first of all, the frequency of the current at the rotor side is not the same as that at the stator side. And from the previous discussion, we have derived already an expression for the synchronous speed, which is 120 F over P. So from this expression, the stator frequency, the frequency of current at the stator side, Fs is equal to, after rearranging this expression, it is equal to P over 120 into Ns. Since the stator is a stationary part of the induction motor, so we can write Ns minus 0, and 0 is the mechanical speed of the stator, and Ns is the synchronous speed, which is the speed of the revolving magnetic field. Similarly, we can write similar expression for the rotor, the frequency at the rotor side, which is Fr, and it can be represented by P over 120 Ns minus Nr. So if we divide this expression with the Fs, so we will get Fs over Fr, and all the terms will be cancelled out apart from Ns minus Nr and Ns at the denominator. And this mathematical expression is equal to the slip. So slip is defined as the relative difference of the state synchronous speed and the rotor speed. So we can write Fr is equal to Sf1, or if F2 is the rotor frequency and Fr is the frequency at the stator side, then F2 is equal to Sf1. So this is the first very important expression. And secondly, the induced EMF in the induction motor is directly proportional to the slip, because in case of a three-phase induction motor, the magnetic field is constant, but this magnetic field is actually revolving at a synchronous speed. And the reason behind this constant and revolving magnetic field is that the three-phase winding across the stator of an induction motor are lying at some angle. For example, 120 degrees for the case of three-phase and 90 degrees for the case of two-phase AC supply. So in this case, the net magnetic field will be constant, but it will be revolving at a synchronous speed. And in order to induce the EMF at the rotor speed, there should be a relative difference between the speed of the induction motor and between the speed of the magnetic field and the mechanical speed of the rotor. If there is this such a relative speed difference present between synchronous speed or the magnetic field and the rotor, then at every instant the flux or the magnetic field will be changing, which is linking with the rotor. So whenever there is a changing magnetic flux linking with the rotor, there will be induced EMF. Now, if the speed of the magnetic field and the speed of the rotor, they are equal, then there will be no relative difference and there will be no rate of change of flux. And in that case, the induced EMF will be equal to zero. And in that case, there will be no current flowing through the rotor windings. So if there is no current in the rotor winding, there will be no torque, because the principle of an induction motor or principle of every motor is that whenever a current carrying conductor is placed in the magnetic field, it experiences a torque. So in order to uh, ensure a current is flowing in the rotor winding, there should be a changing magnetic flux, and that changing magnetic flux is possible whenever the rotor mechanical speed is slightly different from the synchronous speed. So the induced EMF across the rotor side in this case will be directly proportional to the slip. So we have to write E2 is equal to SE1, and if the slip is zero, there will be no induced EMF, and E2 will be equal to zero, and otherwise E2 is equal to SE1, and the magnet maximum induced EMF across the rotor side will be equal to the induced EMF at the stator side when the slip is 1, or when the rotor speed is 0, or at the starting condition. So these are some fundamental concepts behind the equivalent circuit of the induction motor. So from this equivalent circuit, we can write the expression for the rotor current, which is equal to SE2, and this SE2 is basically induced EMF at the rotor side divided by R2 square plus SX2 square. Now, where has this S come from? S is basically the slip, and we know that at the rotor side, the frequency is directly proportional to the slip. So Fr is equal to S times F1. So if we consider same frequency across this whole circuit, then we have to write this F1, we have to write this S separately. Okay, so if the frequency is considered to be F1 over here, so we have to write SF1 over here. So when we take S as common, then this reactance will become JS omega into F1. Okay, so S is taken as common. So this reactance actually is a function of frequency. So we have to take this S as common, and it will be separated from the rest expression of the rotor reactance. Similarly, this S has uh, written separately with E2 because E2 is also proportional to the slip. So this is the expression that we have obtained from this equivalent circuit. So if we divide this whole expression with S at the numerator and the denominator, this will become E2, and here we will have R2 over S square plus X2. So another thing which is very important is that the slip is a variable quantity, and it actually depends on the load. So whenever there is a high load, the slip will be high. If the load is minimum, the slip will be minimum. So slip is a variable quantity, and since this slip is appearing across this reactance, so we have to specify this reactance as a variable reactance. So this arrow is dealing with that. And when we modify this expression, the new expression will become this. So here the slip now is appearing with this expression of the resistance, rotor resistance. So based on this expression, we have to modify our equivalent circuit of the induction motor, and it will become like this. So it will become JX2, this E2 which was previously SE2, it will become E2, and it is written over here, and R2 will be replaced with R2 over S. Now, since slip is a variable quantity, so we have to put a variable resistance mark over here. So, simplified equivalent circuit of the induction motor can be drawn by referring the rotor quantities to the stator side, as we have done for the transformer. So in this case, the all the parameters across the rotor side will be represented by the prime symbol, all and the current as well, and these windings will disappear. So this is the new equivalent circuit, and this is JX2 dash, this is R2 dash over S, and this is I2 dash, and these new transformed quantities can be represented by these expressions. R2 dash is equal to A square R2, I2 dash is equal to I2 over A. Since all these expressions from the rotor side are referred to the stator side, so this transformation will be applicable. Here A is the turn ratio, and it is defined as the stator turns divided by the rotor turns. So now we can calculate the power which can be generated by this induction motor. So in order to calculate this power, this equivalent circuit and its understanding is essential. So input power which is drawn by the motor is equal to I1 square into R1 plus R2 dash over S. So these reactive components, all these reactances are basically a sources of the reactive power which is oscillating in the induction motor. Only the power which is drawn or which is dissipated across the induction motor are the powers which are dissipated across these resistive components. Now, this resistance RC is actually very high, and the current across this shunt branch will be minimum. So we can safely ignore these components, and only this stator resistance and this rotor resistance uh, they will be taking part in deciding the power dissipated across this induction motor. So input power will be equal to I1 square, which is the total current, and in multiplied by all the resistances in the circuit. So R1 and R2 dash over S. Similarly, the power which is lost across this induction motor is the power dissipated across the stator winding and the rotor winding. So I1 square R1 plus R2 dash. Now R2 dash is the rotor winding resistance and R1 is the stator winding resistance, and the power dissipated across these windings is actually the power loss. Now the output power is equal to the input power minus the loss power, and after doing this subtraction we will get I1 square R2 dash into 1 minus S over S. So this is the output power, and the three-phase power can be calculated by multiplying this expression with 3. And now we have to calculate the torque which is produced by the motor. And the torque, three-phase power is equal to torque times angular velocity, and torque is equal to three-phase power divided by the angular velocity. So by putting this expression of P three phase and this omega r, we can simplify the expression for the torque, and three phase power is equal to 3 I1 square into 1 minus S over S multiplied by R2 dash. And now this is omega R, which is the rotor mechanical speed of the induction motor. So this omega R is actually written as 2 pi n r over 60. So when nr is represented in rpm, this expression is 2 pi nr over 60. If this nr is in rps, then omega r is equal to 2 pi nr. And the slip can be defined as ns minus nr over ns. So after rearranging this expression, nr can be represented as ns minus sns, and this is equal to 1 minus s times ns. So putting this expression of nr in this equation, omega r is equal to 2 pi by 60 into 1 minus s times ns. So this expression of omega r can be substituted in this expression, and it will become this formula. So here 1 minus s will be cancelled out, this 1 minus s, and 60 times 3 is 180 by 2 pi I1 square R2 dash over this s will come here, and it is s n s. So this is the expression for the torque. Here we have to find out the expression for I1, which we will substitute here, and we will get the final expression for the torque. So I1 is equal to V1 magnitude divided by the overall magnitude of the resistances and the reactances. So R1 plus R2 dash over S whole square plus X1 plus X2 dash whole square, and its square root. So this expression has come from this equivalent circuit, and it is very simple and straightforward. So torque will be equal to 180 over 2 pi will become 90 over pi. This is ns, and r2 dash over s, and I1 square is equal to v1 square divided by this expression, and this under root will be cancelled out. So when we try to plot this expression of torque at various rotor resistances, we get these curves, and these curves are taken for the torque with respect to the slip. So if we vary this slip from 0 to 1, we get such a curve for a given value of rotor resistance. So if the rotor resistance is high, then this type of torque curve is obtained. If we slightly reduce the rotor resistance, the torque curve will be shifted like this. For even smaller values of rotor resistance, these torques will be obtained, which are given over here. Now we can see that in all these cases, the maximum torque is constant, but the slip for the maximum torque is different. Okay, so maximum torque value is same, but for the value of rotor resistance equal to 1, the slip is small. And if we increase the rotor resistance, the maximum torque is same, but the slip corresponding to the maximum torque is slightly increased, and so on. So this Tmax, which is the maximum torque, is also called the pull-out torque. And these curves, I will show you later how these curves can be obtained for different values of rotor resistances. So this is the simplified equivalent circuit again drawn for the induction motor, and here we have replaced the prime terms with non-primes. So jx2 dash is replaced by jx2 because it is straightforward that when we have no mutual inductances between the stator and the rotor side, then it is straightforward that the rotor quantities are referred to the stator side. So we can ignore these prime terms and we can assume that all these terms are referred to the stator side. So this resistance which corresponds to the eddy current loss is also ignored because its value is very high and it actually represents the heating loss across the core of the induction motor. So if we ignore that resistance, we get such a system. So now we have to calculate the converted power and the power in the air gap to calculate the induced torque across the induction motor, and for that purpose we have to draw the Thevenin equivalent circuit of this induction motor. So Thevenin equivalent circuit can be drawn by opening this rotor side, okay, and assuming that the voltage across this open circuit is V Thevenin and all these stator parameters will be the same. Now the air gap power and three-phase air gap power is actually the power which is dissipated across this rotor resistance, and a power dissipated across this resistance is equal to 3I2 square R2 over S. Now we have to calculate V Thevenin. Okay, so V Thevenin from here is actually the voltage dissipated across this magnetizing reactance. So Zm divided by this Z1 plus Zm multiplied by V5, which is given by the voltage divider rule. So this is V Thevenin, and Zm is equal to Jxm, and Z1 is equal to R1 plus Jx1, and again Zm is equal to Xm. So this expression will be obtained. So when we take the magnitude, it will become Xm and it will become R1 square plus X1 plus Xm whole square under root. So this is our V Thevenin. Now we will calculate Z Thevenin. So Z Thevenin will be calculated by short circuiting this input branch and measuring the impedance from this side, from this output terminals. So this is the Z Thevenin, and from this circuit, it is clear that Z Thevenin is equal to the parallel combination of Jxm and this R1 plus Jx1. So this expression can be expanded like this. So their parallel combination will be this term multiplied by this term divided by this term added in this term. So R1 plus Jx1 plus Xm, and we, in order to get eliminated from this imaginary part, we have to multiply and divide the conjugate of this term. Okay, so it will become like this. So, and when we multiply this term with this and this term with this, we will get R1 square plus X1 plus Xm whole square, and similarly these terms at the numerator will be obtained. Now this R1 is very smaller than X1 plus Xm. This is the first assumption, and secondly this Xm is very greater than is this X1. Okay, so by assuming these conditions, we can simplify our expression for the Zthevenin here. Since R1 is very, very much smaller, so this R1 square will be further minimized and this term is ignored and it is represented by this downward arrow. So similarly, this R1 is very, very much smaller than x1 plus xm, so this term will also be ignored. These two terms will be cancelled out, and at the end we get only this real part and this imaginary part, and this real part is actually corresponding to the R Thevenin, and this imaginary part is corresponding to the X Thevenin. So this is R Thevenin and this is X Thevenin, but now x1 plus xm will be cancelled out with this square and we will get x1 xm divided by x1 plus xm. Again, xm is very, very greater than x1, so this x1 will be ignored and we will get x1 xm over xm. Now these two xm's will be cancelled out and at the end we will get x Thevenin equal to x1. So after obtaining this equation for Z Thevenin, the final Thevenin equivalent circuit is drawn over here. So this is V Thevenin, this is Z Thevenin, and this is Z2. So here this is I2. So all these Thevenin analysis is done to calculate the equation for the rotor current. So when we obtain this rotor current, we can calculate the induced torque. So this rotor current is equal to V Thevenin divided by Z Thevenin plus Z2, and this induced torque is equal to P air gap over omega S, and this is equal to 3 V Thevenin square R2 over S divided by omega S into R Thevenin plus R2 over S square plus X Thevenin plus X2 whole square. So what actually we have done, we actually have substituted the value of this P air gap, and this P air gap was equal to 3 I2 square R2 over S. So 3 I2 square R2 over S. So 3 and I2 square and R2 over S. So this is R2 over S and I2 square is actually the square of this term. So this is V Thevenin square and this omega S is present over here, and this Z Thevenin plus Z2. So Z Thevenin is equal to R Thevenin plus JX Thevenin, and this Z2 is equal to R2 over S plus X2. So the real parts and imaginary parts will be added together. So and we will have an under root square root over here as well. But when we take the square, since we have I2 square, so that under root will be cancelled out. So this is the final expression for the induced torque across the induction motor, and if we try to analyze the losses which are taking place across the induction motor, then such a figure will be very helpful. So this is the input power, which is three-phase power, and it is equal to under root 3 VTIL cos theta. Cos theta is actually the power factor. This is the line current, and these are the terminal voltages. P out is equal to P out should be the mechanical power, so it will be low torque multiplied by the mechanical speed of the rotor. So the first loss which appears across the motor from the stator side is the stator copper loss. Then we will have core losses, and after the core losses there will be magnetic field that is actually present in the air gap. So at this stage we have the air gap power, and after the air gap power, that magnetic field actually links with the rotor and EMF is induced across the rotor winding. So the next loss at this stage is the rotor copper loss, and after this rotor copper loss, the power is termed as the converted power. Okay, so this is the converted power, and the torque corresponding to this converted power is called induced torque. And after that point, we have mechanical power. So friction losses and windage losses will appear at this stage, and after this we have other miscellaneous losses. And after subtracting all these losses from the input power, we will get the output power. So hopefully you have understood the concepts which are discussed in this lecture. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.